In this video, we continue our review of the different interaction phenomena between a structure and a fluid at rest. This time, we'll focus on the effects of viscosity. We will therefore remove one of the assumptions made so far, which was to consider the Stokes number large. Only the compressibility of the fluid will be put aside by imposing K very small. We are back in the schematic view of the problem. We consider that K squared is small, which leads to the incompressibility condition divergence of U prime equals 0. This allows us to neglect one of the viscous terms. Moreover, since the momentum conservation equation at order 0 is independent of the other equation which deal only with the fluctuations, we can leave it aside in this study. Here is the set of equations with which we will work. We also recall the expression of the Stokes number. We can make a first observation with regard to these equations. In the momentum conservation, the velocity appears with two different orders of time derivative. This has the consequence of introducing a timescale specific to the dynamics of the fluid. This was not the case before, and the fluid responded instantaneously to the solicitation of the solid at any point in space. To advance a little further with the intuitive approach of the effects of viscosity, let's take a closer look at the fluid stress on the interface with the solid. The addition of viscosity introduces a stress which varies like the velocity, whereas in the absence of viscosity, we only add a part proportional to the pressure, which itself varies like the acceleration of the solid in a viscid study. We therefore expect to see force applied to the structure that are proportional to the velocity and therefore added damping. This remains to be demonstrated. We are going to describe a little more precisely what happens in a simple configuration for which the fluid forces are only due to the viscosity. We consider for that an infinite plate animated by a time-dependent motion along Ex. Two particular cases of motion will be considered. The first one corresponds to the impulsive motion of the plate. This is a classical problem of fluid mechanics called first Stokes problem. We describe the motion as follows. For negative t, u equals 0. For positive t, u equals u naught. For the second problem, we will look at the motion of the plate at the frequency omega naught for the displacement amplitude psi naught. We write the displacement of the plate using a complex harmonic function. It will be possible in the following to work directly with this complex function, remembering that the physical solution of the problem will be the real part. It will be the same for the velocity, for example. These problems can now be scaled. On the left, for the plate set in motion at velocity u0, we have a characteristic velocity available for scaling. The dimensionless velocity of the plate is thus equal to 1, which provides a boundary condition. By choosing an arbitrary length L, we end up with the problem described by the momentum conservation equation in which the Reynolds number appears. Given the form of the boundary condition, we will look for solutions of this problem in the form of a velocity depending only on y and oriented along Ex. In the case of the second problem, the dimensionless version of the imposed displacement is a motion having the displacement number d as amplitude. The frequency of the oscillation is equal to 1 once the problem is scaled, hence the complex harmonic function E minus it. The dimensionless momentum conservation equation is identical to the other case, except for the presence of the Stokes number instead of the Reynolds number, since a characteristic velocity based on the oscillation of the solid and its size has been used, rather than the velocity u0. Here again, we will look for solutions in the form of a velocity function of y and t only and oriented along Ex. Let's start with the first problem. We start by decomposing the momentum conservation equation along x and y, and we assume that the problem is independent of x since the plate is infinite and the boundary conditions are independent of x. The second line tells us that the pressure in the fluid is constant. it does not play any role in the problem. Finally, the solution involves only the scalar field Ux, and the equation governing this field is a diffusion equation. It must be solved with boundary conditions and initial conditions. Ux equals 0 everywhere for t negative, and Ux in y equals 0 is equal to 1 for t positive. The solution of this classical equation is given here. We find that Ux is 1 minus the error function of the square root of 1 over 2 Reynolds over time. The error function is 0 for x equals 0 and tends to unity for large x. The velocity dynamics described by this solution is now animated. The dark blue lines are the instantaneous velocity vectors. Delta is the length at which the velocity is below 1% of the plate velocity. It defines a boundary layer thickness that grows as the square root of the time divided by the Reynolds number. We can also calculate the dimensioned version, which is 4 times the square root of t nu. This boundary layer induces a shear at the wall which is very large at t equals 0 and decreases with time. We have just highlighted the process of diffusion of the tangential velocity at the wall inducing shear forces on the plates. Let's illustrate this on an everyday experiment. Here are 2 fresh eggs. The one on the right is plunged into boiling water to obtain hard-boiled egg. Once cooked, the egg on the right can be seen as a solid body, while the one on the left is made of a rigid wall, the shell, with a very viscous fluid inside. If we attempt to impulsively rotate the egg, we create an initial condition similar to the first Stokes problem described above. We see that the raw egg initially takes the given impulse and rotates very gradually as long as the whole fluid inside is driven by shear. The hard-boiled egg, on the other hand, starts to move instantly and rotates much faster. The diffusion process does not take place as it is a solid body. We can now do the opposite experiment. After having rotated the raw egg so that it turns as quickly as possible without making it fall, let us try to stop it suddenly before releasing it immediately afterwards. The egg starts again because the fluid inside did not stop immediately. The process of viscous diffusion gives back the momentum to the shell. And if we perform the same experiment with the hard-boiled egg, obviously it does not restart. Let's see what this viscous diffusion process does in the case of a structure oscillation. This is the second problem. We can also show a diffusion equation for the tangential velocity Ux. The displacement is of amplitude d and directed along Ex. It is an oscillation with a frequency omega equals 1, that is psi prime equals e to the minus it. This imposes a velocity at y equals 0 equal to minus e to the minus it, which is simply the derivative with respect to t of psi prime. We add a condition at infinity. The perturbation must tend to 0 when y tends to infinity. We will solve this equation by looking for solution in the form of propagating waves in the y direction. Let us consider 2 waves of unit frequency and amplitude a and b, whose wave numbers are unknown at the moment. Putting this form of solution in the diffusion equation and retaining only the wave which does not tend to infinity when y tends to infinity, we find the value of the wave number k and the amplitude of the remaining wave from the boundary condition. We find a solution in the form of a wave propagating towards the positive y and whose amplitude decreases exponentially when we move away from the plates. Here is what this solution looks like. It highlights the fact that the fluid is driven by the viscous effect on a layer of a certain thickness, which we will discuss later. Let us now calculate the fluctuation of the stress at the wall. We can then calculate the surface force as the projection of this stress onto the modal motion, that is Ex. the surface stress is simply dF prime times the displacement number. We will use this result to calculate the resulting force on the square plate of dimensions L times L. The force in physical units is rho omega naught L power 4 times dF. All calculations done, replacing the dimensionless parameter by the quantities of the problem, we find a force where appear a term proportional to the acceleration and a term proportional to the velocity. So we are dealing with an added mass and an added damping. We can rewrite these two quantities by highlighting a characteristic length delta equals square root of nu over 2 omega naught, which can be seen as a boundary layer thickness. This is the thickness of fluid moved by the solid in the oscillation. We see that the greater the viscosity, the greater delta. On the contrary, the greater the frequency of oscillation, the smaller the thickness of the fluid. Thus, the moved fluid layer is small and the added mass decreases. On the other hand, even if this fluid thickness is small, the shear can become very large and therefore the damping effects as well. This appears in the damping coefficient, which has omega naught in factor. In conclusion of this video, we have highlighted an effect of moved fluid layer which leads to a purely viscous added mass phenomenon. Energy is also transmitted to the fluid by diffusion, which leads to an added damping phenomenon. We have shown that the importance of these effects is quantified by 1 over square root of the Stokes number. During oscillation, we have shown that the thickness of the moved fluid zone varies as the square root of nu over 2 omega naught.